Well, good evening, everyone. In order to keep us on track tonight, I am going to get started. And for those other participants that are looking forward to joining tonight, we will let them into the presentation as we move along here. So I would just like to start out by welcoming everyone to our third virtual Return and Learn of the spring semester. My name is Justin Durenzis. For those of you who do not know me, I serve as Assistant Director of Alumni and Parent Engagement here at the college. And before we get started tonight, I just wanted to go through just a few things that will make sure that our presentation goes smoothly. So if I can ask everyone to please keep themselves muted at all times throughout the presentation, this will definitely help to cut down on any background noise. Tonight's presentation is being recorded. So if you do have your camera on, that is fine. I just ask that you be mindful of any excessive movements that you make in the background, as this may be distracting to Dr. Malenda tonight, who's our guest presenter. And as we move throughout the presentation, I would like to let everyone know that if they do have any questions as we move throughout the presentation tonight, to please add those into the chat box. Dr. Malenda and myself will monitor that chat box as we move through tonight. So please don't hesitate to drop any questions that you may have in there. I would now like to introduce our guest presenter this evening, Dr. Ruth Malenda. Dr. Malenda teaches courses in introductory physics and modern physics. Her research interests are in theoretical modeling of atomic and molecular physics, which she has used to study processes such as collisions between atoms and molecules. And she has recently started work in astrophysics. So this presentation tonight, hopefully she will be touching on a piece of astrophysics throughout the presentation. She is also a member of both the American Association of Physics Teachers and the American Physical Society. So without further ado, I'm going to turn it over to Dr. Malenda.
Hi, everyone. I'm so glad to be here with you this evening, and I'm so glad to see friendly faces. It's very exciting. I'm just going to move some stuff around and share my screen. So let me see. All right, I think you should be able to see that now. Yeah. Perfect. Great. And I will try my very best to keep an eye on the chat, but if I miss anything, Justin's going to flag me down so I don't wait too long before I get to your questions. Okie dokie. All right. I'm really excited to be here and talk with you guys tonight and talk to you about some of the opportunities that our students have to take a look at astrophysics and astronomy here at Moravian College. So just kidding. There we go. So I thought maybe I'd start out telling you guys just a little bit about me. I'm from Fleetwood, Pennsylvania, which is about an hour west of Bethlehem. I did my undergrad at Kutztown University, and I went on to graduate school from Lehigh University, and I graduated in 2012. And then I spent a year at Lebanon Valley College before I came to Moravian College in 2013. And so, as Justin said, I'm actually a theoretical atomic and molecular physicist by training. That's what I have my PhD in. But for some reason, I said, oh, do you guys want to hear about theoretical atomic and molecular physics or astrophysics? And they all said astrophysics. So I said, okay, I guess that's what we'll talk about. So normally I use quantum mechanics techniques to study atoms and molecules and how they interact with each other. And I really love doing this work with my students. But my area of expertise is somewhat limiting in some respects because we only teach our upper level classes every other year. And so what that means is that I only get to teach quantum mechanics every other year. And what that means is that every other year I have junior students who might be able to do some quantum mechanics research with me. And so I love doing research with students, and I've had some really excellent students in the past who've worked with me on some of that. And we've presented at conferences and published papers and things like that, but it is a little bit limiting in terms of who that work is available to. So when I learned that there was a chance to get some background in astrophysics so that students could start doing research like right after their freshman year, I knew that that was something that I wanted to be involved with. And plus we get to look at stars and astrophysics and all that really neat stuff. So I was really excited to get on board. So a quick outline of what I'll be talking about tonight. I'm going to start with the Moravian College online course that I took so that I could learn the techniques that I'll be using, photometry and some of the astrophysics research that we're doing. And then I'll discuss some of the work that Brian Kelly and I worked on. Brian's actually here. He did a SOAR project with me, and then that continued into an honors project. And we worked with my friend Phil Reed at Kutztown University on that work. And then finally, I get to take a sabbatical next year. I'm super excited. And so I'll spend a little bit of time talking about my plans for my upcoming year on sabbatical. So the research in astronomy course that we took, I'll talk a little bit about the Mars Desert Research Station Remote Observatory. I'll give you a little bit of a background on photometry, and then we'll talk about the different types of variable star systems that we can actually use this to take a look at. So Earth Science 293 was a completely online half-unit course, and it was taught by Peter Detterline, who is an astronomy professor at Montgomery County Community College and director of the planetarium in Boyertown School District. He is a friend of Gary Becker, who has been teaching our astronomy course in the physics and earth sciences department for years. And he's the writer of Star Watch, if you guys know Star Watch. And he was instrumental in setting up and getting Moravian College access to the remote observatory that we're going to be talking about. I actually took the class with Dr. Kelly Kriebel, who's also here. He's the chair of our Physics and Earth Sciences department. And we took the class in the fall of 2018, and it was us and 4 physics majors and several other students who were enrolled in this course. And one thing I have to mention here is that at the time, I was really excited to be learning about photometry and astrophysics. What I didn't realize was how thankful I would be that I had taken an online course, right? So I never occurred to me that I would, value having taken an online course, but having been in a class that was well thought out, well organized, and having that as an example when we jumped online over the course of a weekend last year, about a year ago today, when we had to figure that out, it was really valuable to have had that experience and to have seen from a student's perspective what it's like to have to take a class that's online. And so I'm forever indebted to Peter for that example when I took that class with him. And so at the time, I was excited to learn about astrophysics, but I didn't realize it would have the added benefit of giving me perspective and insight when I had to teach online. In terms of the material we covered, we learned about the basics of photometry and how to run the telescope. Telescope, you say? Why, yes, the telescope. So this all started when Gary Becker approached Kelly Kriebel, our chair, about a plan to get Moravian students access to a telescope for research. Gary and Peter are members of the Mars Society, which was working on setting up a robotic observatory at the Mars Desert Research Station in Hanksville, Utah. And so I got a little map over here so that you guys can get some perspective of how just in the middle of nowhere Hanksville, Utah is. We've got Salt Lake City, Las Vegas, Albuquerque, Denver, and then smack dab here, we've got Hanksville, Utah. And then we've got a picture over here that's showing, I believe this is a different observatory, and then this in the red circle here is actually the remote observatory that Moravian students have access to. And so they said that if Moravian College invested in this project, students at Moravian would have access to 25% of the observing time. All of the observations, though, would be done remotely. So even though this is out in Hanksville, Utah, far, far away, you could sit on your comfy couch in your PJs and you could set this up so that it would run and take images for you to analyze. And so I'm incredibly thankful that Moravian was willing to make the investment, and I have seen the benefits already, and I know that it's going to be beneficial for students for years to come. So I just included some snapshots. With the funding secured, the work got underway and the telescope was built and set up and brought online. And here we've got our intrepid Gary Becker out in Hanksville. And over here is an image of Peter working on getting the telescope set up and mounted. This picture I found really just gives you like a nice perspective of what it looks like there, right? It really does very much look like Mars. So I don't know if you guys have seen those recent pictures that have come back from Mars, but that's pretty much what it looks like. And then over here, actually, this is Peyton Zenkel, and Peyton is currently a senior physics major at Moravian College. And Peyton went out to the observatory with Gary and Peter. I believe it was the summer after we took the course about research in astronomy. And so this is just giving you an idea of the observatory that we have access to and what we can use to actually take these images and do this research. The observatory has two instruments. The one that I mainly have used is the one that's used for photometric research, which is a 14-inch telescope with ultraviolet blue, visible, red, and infrared filters. They also have an astrophotography instrument, which is a wide field 70mm refractor telescope. I haven't used that quite as much, but in fact, this background that I'm using for my talk is an image I took during the class of the Veil Nebula. And so you can kind of see this wispy thing through the middle here. This is a picture that I took, and essentially what you do is you take 3 different images with 3 different filters, and then you recombine them to form a single image. And so this is one of the projects that I did in that course that I took. So now that we have a little bit of an idea of the instrument that we have access to and that we're able to use, I'll tell you a little bit about how do we actually use it. So if you want to work on taking data, you have to use a system called Skynet. And yes, it is Skynet, just like in Terminator. That's what they went with. And so I've got a little snapshot of what it would look like in Skynet. There, right here is where you would enter in the observatory you want to use. Down below, you would enter the instrument. So for us, we would pick the 14-inch telescope. And over here, you can see it says target lookup. And so you would enter which star you were interested in observing there. And you would tell it when you want to be doing your observations. And if you would scroll down on this page, you would see something called a seeing profile that tells you if your object is going to be visible when you want to do your observation. And so if you get something like this, it means you're not going to be able to see anything. We're looking for a line that's going to be above this black horizontal line right here. And if it's above there, then we know that we're going to be able to have a chance to see the target that we're interested in during the time that we're making the observation. So you go make some adjustments, pick a new target, pick a new date, and you might get something that looks like this. And now what we can see is the blue line, and we see there's just a little bit above that horizontal line here. And so that's probably not enough time. You probably want to give yourself a little bit of cushion in case there's problems with weather, or in case you need to take multiple exposures, something like that. And so make some more adjustments. And now you would have a good seeing profile. And so here we can see that there's a lot of target visibility during the time when we would want to take these observations. And so this would be, this would tell us that our observation is good to go. And then the next step in the process would be you would want to select the filters, the number of exposures, the length of exposures, and the amount of time between the exposures. That's all going to depend on what type of target you're looking at. So if you've got an object that has a really fast period for its changes, you might want to do a bunch of observations over the course of one evening. However, if you've got something that has a long period in its changes of maybe a couple of weeks, you might want to take one observation every night over the course of those weeks. And so you would set all that up to run. And if everything works out perfectly, you might get a nice image like this that you could then analyze. And so we were using a technique that's called photometry, which basically measures changes in a star's brightness. And it's used to study stars with changing magnitude. And so those are usually referred to as variable stars. I'm going to first tell you about the process of photometry, and then I'll tell you a bit about the variable stars that we can actually study with this technique called photometry. We use a program called AstroImageJ. So here's the image we have from the previous slide. The first thing that we have to do is we have to identify our target star on here. And I've got to tell you that as an amateur astronomer, like very new to this was sometimes the hardest part of the process for me. I know that sounds silly, but like I would look at this and I would have no idea where my target was supposed to be. So we would go to a database and we would get something called a star chart. And your target would be this little guy right in the middle of the crosshairs, and it would give you some of these comparison stars all around it. Now, it sounds like it should be easy to figure out which one of your stars is the target stars, but sometimes your star chart would be scaled differently. Sometimes it would be inverted, sometimes it would be rotated. And so there were actually a lot of different permutations that you could get until you figured out exactly where your target star was on here. Once you're sure that you're in the right orientation and everything looks roughly like it should, the next thing that we would usually do is try and identify a cluster of stars that are easily identifiable. So for instance, if you look down here in the corner, you can see 3 stars on top of each other, or 3 stars making a little triangle. And so then you would identify and you say, okay, that's probably these 3 stars right here. Don't they look pretty similar? And then you would say, okay, and then this guy over here probably is something like that. And so you would say, okay, my target star is something like up in here. And indeed, if you look, here's our target star circled in green. And then we've got some of these comparison stars on here so that you can kind of see how it's different from the star chart, but close enough that you would have to be able to identify those. And so once you're able to do that, then you would use our program AstroImage-J, and you would select your target star, and that's what we see here in green. And then you would select several comparison stars. And so what AstroImage-J is trying to do is it's trying to take stars with known brightness and then compare the target star to those known brightnesses so that you can get an idea of what the brightness of the target star is. And so I've got a target star here, and I've got a comparison star up here and a comparison star here. And you would try and get as many comparison stars as you can in order to get the best value for your target star. So one image will tell you about the brightness of the star at one point in time. But what we really want to do is we want to figure out what the brightness of the star is doing over time. And so that's where we use something called a light curve. And so a light curve is where you plot the brightness of the star versus time. And so what's happening in this image is each one of these little black dots along here is one observation, one image that we would analyze with AstroImage-J and get the brightness for that star. Okay. Now it's not as hard as it kind of sounds. The program is really, really smart, and you can set up a series of images and it'll run through each of those images once you've picked your target and your comparison stars. And it does that pretty automatically if you've got everything set up correctly. And so as you can see, we've got the brightness changing over time. So that's great. Now we know how this star, this target star, is going to change over time. But what good is that, right? Like, why do we want to know that? And so it turns out that this analysis is really helpful if you've got systems that we call variable star systems, where the brightness of those stars change over time. And there's actually quite a few different types of variable star systems. So I'll tell you a little bit about those now. Asteroids is one of the obvious ones, right? And so this is an image where we've got some asteroids. Asteroids, it's the location of the actual star that you're seeing. And when we say star, we're using that a little bit loosely here, right? Because this is an object that's reflecting light. It's not actually producing its own light. And so you can see down in the corner here, we've got an asteroid that's changing position through the sky. And actually there's another asteroid up here that's doing a little bit of wibbly wobbling around as well. So that's one example. Periodic nova are another example. And so normally we're used to thinking about the idea of like supernova. And so supernova would be these big giant explosions. And we tend to think of them as pretty final and pretty finite. But it turns out that sometimes there are systems where you've actually got 2 stars, and usually you have a smaller, hotter star that's in this, what we call a binary system. And they're so close together that you're larger main sequence star is actually transferring mass to this guy. And so once the temperature gets hot enough in the small hot star, it undergoes a thermonuclear reaction, which we know as a nova, and it explodes and blows out all of this material. And so you get this big bright change in the brightness of the star all at once. And this can happen over and over again. It doesn't just necessarily happen once. You can get this mass transfer happening over and over again. And in fact, it can happen on the order of a couple hundred days, and you can see these periodic nova undergoing supernova. This is one of my favorite types of systems, and one that I'll talk a bit more about when I talk about the work that we did with Phil Reed at Kutztown University. In this case, we've got two stars that are orbiting each other. So this is a binary system. And one thing that I should point out is when you look at this system, you don't see two stars. It's not like you see two bright spots. You see one bright spot, okay? And so if you were to just look at it, it would look like it's one single star. However, if you look at the light curve, so down here is plotted a light curve with its relative flux over its orbital phase, you can identify that this is actually a binary system. And so what you can see is these stars go around each other. When the small bright star gets blocked, so here it comes, you see this large dip because we get a lot less light from this system during that part of the eclipse. And then the other part that we have is when the larger but dimmer star gets blocked, we get this over here, what's known as a secondary eclipse. So even though these two stars are too far away to be able to resolve two objects, we can tell a lot about the stars by using the photometry and looking at how the brightness of the system changes. This one is the one that usually gets people like really excited, is the idea of exoplanets. And so exoplanets are when we find planets that are in a solar system outside of our solar system. This is another example of an object moving in front of the star, and that's what's causing the change in the brightness of the light. Now, an important thing to note here is if we look again, I've got, there's this plot of flux, which has to do with brightness over time. If you look at the shape of this, it's very different than what we saw on the previous light curve for the binary stars, right? That had that deep, sharp V and then a little guy over at the other edge for the secondary eclipse. This has a pretty abrupt fall off, and then it's got kind of a plateau for when the planet is completely in front of the star, and then it goes back up. And so this is called the ingress, and this is called the egress on this side here. And so this is a pretty characteristic shape for if you have an exoplanet. And so that's going to come back in a little bit as I talk about some of the work that we did later on. The other thing I'll mention here is I haven't done any work like this, but I chose this animation because I thought it was really interesting as I was doing some research and reading about this. This is showing the light curve for 3 different filters. It's got red, it's got green, and it's got blue. And the way that they're actually using this is they're using the differences in these 3 different light curves to give them information about the atmosphere of the planet, which blows my mind, right? That's crazy. So here we have this thing that's a planet that we can't see directly. So you can't observe something that doesn't give off light directly, but we can tell it's there because we can look at the light curve. And then these guys are so smart that they figured out that if they look at these different filters, they can figure out the atmosphere on another planet in a different solar system based on that, which is just incredible to me. So I thought that this was a really, really interesting image to share with you guys. This guy is a bit involved. So if you will indulge me, I have to talk a little bit about something called spectroscopy because it has connections to my theoretical atomic and molecular background. So I'll try and break this down and explain it piece by piece so that we're all on the same page here. So one thing that you should know is that you're not always going to be able to see a change in the light curve because of an exoplanet. If the planet is really tiny, it's not going to block, or really far away, it's not going to block enough light from the star for you to actually be able to detect the dip. But there's other ways that we can figure out that there's an exoplanet in this system. So what we have down here at the bottom is kind of like the image that we saw on this previous slide, right? So we've got the planet goes in front and then it goes away. And so here what we've got is the planet is moving in front of the star, and then this is showing it moving away, okay? That would be along our sight line from Earth, essentially. This image up here is what that would look like from above, okay? And we're used to thinking about the sun or the star at the center of this system is going to be this big, giant, immovable object. But it turns out that it affects the planet and the planet affects it. And in some cases, you can actually see that the star is going to be orbiting around its center of mass, and it's actually moving. Now with our solar system, our sun, I believe it's orbiting, but its center of mass is inside of it. So you really don't see the changes in the location of the sun in our solar system. But in some situations, it might be possible to, depending on the masses of the objects involved. And so this over here, sorry, it's a little blurry. This is a speed plot. And so this shows the star moving away from us and moving towards us and moving away from us and moving towards us. A lot of times in astrophysics, they use something called spectroscopy. So every single atom, every single molecule has what we call, it's kind of like a fingerprint that we call spectral lines. They all give off very specific, very unique spectral lines. And if you can detect those lines, then you can identify the materials that the system is made out of. And so what's shown down here in the bottom right is a continuous spectrum. So it's got the whole rainbow in the background. And then you can see kind of superimposed on that are these dotted lines. And so that would be an example of the spectral lines that this star would be emitting. And you would use that and you would say, okay, if I see these lines, I know there's hydrogen in there. If I see these lines, I know there's helium in there. But what you notice is that these lines are actually moving, okay? And that has to do with something called the Doppler effect. So that's the last little piece that we need to be able to know what's going on here. And you guys all know the Doppler effect, whether or not you think you do, because you guys have all heard a truck go by and do something like this. Right? It starts off high and then the pitch goes low. It goes. And the reason that it does that is because as it's coming towards you, the frequency increases. And as it's moving away from you, the frequency decreases. And it does that because sound is a wave. Light is also just a wave. So when objects come towards you, they get shifted to higher frequency, or what we call blue shifted. And when they're moving away from you, they get shifted to lower frequency, or what we call red shifted. And that's what they're showing with these spectral lines moving back and forth. As it moves away from you, you get a red shift. And as it moves towards you, you get a blue shift. And you can use the information about how quickly it's shifting and how often it's shifting to learn about how is it moving in this circle? How is it moving towards you and away from you as it goes around that orbit? And so we can't see the planet, but we can get so much information about the mass, the radius, how these objects are interacting with each other just from looking at the spectral lines and how they change over time. So I haven't actually done this, but it's got a lot of roots in spectroscopy, which is something I'm really interested in working more on. So now I'll talk a little bit about the work that Brian and I did with Kutztown University. And I'll start by telling you about the KELT and the TESS missions. And then we'll talk about the Corona Borealis work that we did, and a program that's called Binary Maker 3 that we used for some data analysis. So this is my buddy, Phil Reed, down here. He works at Kutztown University. I think he's been there since before I graduated Lehigh. So he's been there for a little while. And they have this beautiful Grimm observatory that they have that he's gotten up and running. And so Brian Kelly and I went there for the summer, I believe it was summer of 2019. We would go a couple of times a week and we would work with Phil and his students. And we were using KU's observatory to look at possible exoplanet candidates from the KELT and the TESS missions. And we actually used the photometry techniques that we learned in their course at Moravian in order to be able to do this. So I'll give you a little bit of background. KELT stands for kilodegree extremely little telescope. Astrophysicists love acronyms. They love them. It's just true. It's just one of the things that they love. So this was a project that was held jointly by Ohio State, Vanderbilt, Lehigh, and the South African Astronomical Observatory. And as of March 2020 was the last update I was able to find. They had discovered 26 exoplanets with this system of telescopes. And there's an example of KELT North located in Arizona right here. A lot of these are what are known as hot Jupiters. So the exoplanets that they find are called hot Jupiters. And the reason for that is because they're about the size of the Jupiter in our solar system, but they're much closer to their sun. And the reason that that's useful is because they're big and they're close, so they block a lot of light, okay? And they're called hot because they're so close to their star. And so typically they can orbit anywhere from like 2 to 15 days, whereas our Jupiter takes 12 years to go around the sun. So they're a lot closer to their star than our Jupiter is to our sun. TESS is another system that was set up by NASA. It's the Transiting Exoplanet Survey Satellite. And the goal for this program was to survey the entire sky over the course of 2 years, looking for exoplanet candidates. And so this idea of exoplanet candidates is really where we came into play with this research. These telescopes are basically taking pictures of the sky, and they might find variable stars, but they're not going to do the really intensive photometry that's necessary in order to verify that it's actually an exoplanet system. So what they do is they send out a bunch of candidates and they say, hey, this star is varying in such a way that it might be an exoplanet. Can you do some really close observation, some really nitty-gritty observation, and check out and see if that's actually an exoplanet or if it's a false positive? Maybe it's something else. Maybe it's a binary star system or something like that. So the first part of our summer working with Phil, that's what we did, is we got to use our photometry techniques that we had learned with Peter, and we looked at some data that Phil had collected about exoplanet candidates from the KELT survey. So we would perform the photometry, and then we would verify whether or not the light curve was actually for an exoplanet or something else. And so over here, you can see something that does not look like an exoplanet, right? We said that the exoplanet very routinely has a drop off, a plateau, and then it goes back up. And so this we would see, and we would say that's probably not an exoplanet. But if we got something that looked like this with the drop off, the nice plateau, we could confirm that that's probably an exoplanet system. And this work really helped us to hone our photometry skills. I was really glad to have taken the course with Peter. I really appreciated having that background and really, you know, got a chance to sink our teeth into some of this data that Phil had. Unfortunately, we never actually got to learn to use the telescope in the observatory at Kutztown because that summer the dome was being replaced. And so let me see if I can get this to do what I want it to do. There we go. So this is a different shot of Grimm Observatory, and what you can see here is actually the new dome, and up here you can see the old dome. And so Phil was really kind to work with us that summer because he had all of this going on. So while we were coming and we were doing photometry and things like that, he was getting his observatory ready to get the dome switched out, which means he had to prepare all of his equipment. He had to make his telescope safe. He had to like take equipment apart and get it out of there to make sure that it was, you know, okay. And I think that's actually Phil right there. You can tell by the beard and the ponytail. They're testing out the door. And so he was doing a lot of work preparing because they had to do this all in one day. They couldn't take the old dome off and wait because then the whole observatory would be exposed to the elements. So in one day, they had to take the old dome off, and you can see them setting up the crane there, so they could then put the new dome on the same day. So poor Phil was trying to work through all of that summer while we were pestering him and talking about doing our research and stuff. So here you can see the old dome coming off. which is just kind of incredible. And the same day they had to pick up the new dome and put the new dome on there. And I can't get, I apologize. I wanted to play it a little bit faster, but I can't get to my speed controls because the zoom, the zoom buttons won't move out of the way. So there we go. We can see the new dome going up, up, and being put into place on there. So unfortunately, we didn't get a chance to actually learn how to use the telescope that summer because it was busy getting a new hat. All right, so now I'd like to talk a little bit about the next project we worked on with Phil. Phil's main area of research is stellar evolution and interacting binary and triple star systems. And so we worked on a system that Phil really likes called U Corona Borealis, or more affectionately UCRAB, we called it. And this is what we call an algal type eclipsing binary system. The component stars are a blue-white main sequence star and a cooler white subgiant star. And it actually has a period of around 3.5 days. So it's a very quick orbiting orbital period. This is not a gift specifically of that system, but I really liked this because it gives you a good vantage point of what we call an angle of inclination. And so what's happening is the orbit is not exactly along the sight line from Earth. It's kind of at an angle. And you can tell that because as these stars are orbiting each other, they're not completely blocking each other. And so if you watch here in a second, when the yellow star goes in front of the white blue star, what you'll see is you can still see some of the white blue star. So see how you still see it even though it's during part of the eclipse. And so that angle of inclination is one thing that we measure when we look at these different star systems. Algals are interesting because they seem to run counter to the normal stellar evolution. Normally, what they say is the greater the mass, the faster the evolution, and the more quickly it leaves the main sequence and becomes either a giant or a subgiant. In the case of the algals, because you have these two stars, it behaves really differently. Initially, you've got a more massive primary star that evolves really quickly and a less massive secondary star. And after some time, you've got a primary star that gets large enough that it begins to actually transfer mass to the other secondary star. And that changes what we call the mass ratio in the system. And eventually your primary star becomes the less massive star. And what that does is that leads to a less massive, more evolved star and a more massive, less evolved star, which runs counter to what would be normally predicted by stellar evolution. And so your less massive star is already a subgiant, while the star with the greater mass is still on the main sequence. And so this was one of the systems that we were taking a look at. And so this is actually some work from Brian Kelly's honors thesis. So we performed photometry on the data that Phil had taken for UCRAB in, I think, 2018. And here you can see light curves that are in the visible. We got the blue, we got the red, and the IR filter here. And so these are the light curves for each one of these, and you can see primary eclipse and secondary eclipses over here on each one of these images. And they can give you information about mass ratios, the angle of inclination, which I mentioned, the period of the orbit, and the temperatures of the stars. And so that can give you information about the types of stars that are involved. So if we didn't know what types of stars, we could identify them from the information we could get from this. Specifically, we were looking to compare our results to those published in a paper by someone named Yearly in 2008 in this work. You can also get some interesting information if you plot all of those light curves on top of each other. And so what I've done, or what Brian did here really, was he plotted our 4 different light curves on top of each other. And if you look at the 2 different eclipses, that's where things start to get interesting. And so what you can see is down at the bottom here, the lowest in the primary eclipse is actually from the blue filter. And so what that indicates is that we've got a primary star that's going to have more blue light and a hotter temperature. And then up here in the secondary eclipse, you can see that we've got the infrared and the red actually have the largest dips. And that gives us information about the secondary star being the cooler of the two stars. Once we've got the photometry done, we can actually put it into a program that's called Binary Maker 3. And this models the two stars that are orbiting each other. So you can see here in this upper corner is a window that would actually be the two stars as they're orbiting each other. And you can put in a bunch of different parameters. You can put in guesses for temperature, inclination, masses, things like that. And the thing about Binary Maker 3 is that you can also let those variables adjust so that they can do a better and better fit. And so as you can see down here in the bottom, we've got our data from our light curve is the red. So you can see it's kind of sporadic and spotty and there's a little bit missing here and there. But then on top of that is a fit based on our data and allowing some of the parameters to change to do that fit. This is a radial velocity curve. I'm not going to talk too much about that tonight. And so Brian had put all of this into Binary Maker 3. And what you can see here is in each one of these, we've got our data points are represented by the dots. The model based on the yearly values, so the values from that paper, is the black line. And then the fit is a green line that's on top of that. And again, we've got visible, blue, red, and infrared filters here. And at first glance, these look like they're lining up pretty exactly. But if you look a bit closer at the eclipses, you can see that there are some differences. So this is an example. This is the red filter. And what you can see is if we zoom in on the primary eclipse, our data and the fit to our data is lower than the values from the yearly paper. And similarly, if we look at the secondary eclipse, you can see that our data and the fit to our data is higher than the values from the model with the yearly information in it. And again, this is just the infrared. Again, our values are slightly lower in the primary eclipse and slightly higher in the secondary eclipse than they were for the yearly paper. And so that was the work that we had done over the summer with Phil, and then Brian continued as part of his honors work. So now I get to talk a little bit about sabbatical, which I'm very excited to go on next year. So first thing we're going to do is, I don't know if you guys heard, but there's been a pandemic. And so we've been a little busy this past year. And so our first order of business is we're going to sit down and we're going to publish some of the work that we did on the UCRAB system and do that. So that's one of the first things that I'd like to get around to. And the next thing I'm going to tell you about is a program called Phoebe. And then I'll talk a little bit about some spectral data. So Phoebe stands for Physics of Eclipsing Binaries, sort of. I told you they like their acronyms. They're going to make them happen by hell or high water. This is basically the new and improved version of Binary Maker 3. And so you can see this would be a model of a light curve. Over here is a relative velocity plot that I pointed out on the previous slide. And this would be modeling, I believe, the orbits of the two planets. I don't really know much about this software, but I'd really like to. And so that's one of my goals for the upcoming years to learn how to use this Phoebe software so that when we get photometric data, we can analyze it with this. It's really fancy. This is just a snapshot from Phoebe's main page of what it can do. So it seems like it's a pretty powerful program, and I'm excited to learn more about it. And the other area I'm interested in is doing a little bit of spectroscopy. This is an example of something called an E-shell spectra, and this is actually from our sun. And so E-shell spectras get really, really precise information about spectroscopy. And so each one of these rows going across actually represents a different wavelength. And then if you see all these little black bands, those are the spectral lines that I was telling you about previously. And so it's getting a bunch of different spectral lines and a bunch of different wavelength regions. So again, this is from our sun. I just found this picture and thought it did a good job showing it. The real spectra that you would get from the spectrometer would look something like this. It's not nearly as pretty. But this image does do a nice job of showing you what the spectral lines mean. So for instance, this is a sodium line, and it allows you to identify that there's sodium in that system. We've got potassium that they're identifying up here. This is an H alpha line, which has to do with hydrogen bomber series, is down here. And so right now, Phil has a bunch of this data that he has to normalize and standardize by hand. Each time he gets it, he has to go through and normalize his images. And so what he'd like me to do is write some code that makes that process kind of standardized, and you can do it just by running it through a computer program. It's kind of an involved project, and it requires a lot of computer coding background. So it's kind of beyond the range of what an undergrad student is going to really be able to take on if they do it over the course of a year while they're taking classes and doing everything else that they're doing. But somebody on sabbatical with some computer code background, they could definitely help him out. So that's where I come in. And so I would just like to give a special thanks to Peter Detterline and Gary Becker, Brian Kelly, Phil Reed for his help, Peyton Zankel, and Moravian College, and particularly the physics and earth science department, for giving me the opportunity to do this work. And thank you guys so much for having me here tonight to talk to you. And at this point, I'd be happy to take any of your questions.
Thanks so much, Ruth, for your presentation tonight. Really fascinating and interesting information covered. So really appreciate you providing, all of the great work that yourself and the other faculty in the physics and earth science department are headlining. So thanks so much. One question that we did get in from one of your former students, Matt, was actually relating to one of the first few slides that you presented on, and it was the slide regarding the data points. And Matt had a question on what kind of determines that best comparison for the target star. Is it kind of an algorithm or a software that's utilized, or is it based off of preferred best judgment?
There's a variety of things that kind of dictate that. So you want a bunch of comparison stars. You want them to be roughly in the range of the star that you're looking at. So you don't want them to be too all over the place. You'd like them to be a little bit above and a little bit below, so that they kind of straddle the range of your star, and you can kind of pinpoint it that way. So there's a couple of different things that might factor into that. You use different databases to look up the possible comparison stars. And so depending on what stars are in those databases might also dictate that a bit.
Thanks, Ruth. Any of our other participants tonight have any questions that they'd like to put into the chat at this point?
I was telling Justin earlier, I do this every day in class. So I'm like, hey guys, do you have questions? It's okay. I'll wait. Sometimes it takes a minute to come up with questions. I think this was the picture you're referring to, right, Matt? Yeah.
Thanks, Brian. Brian just commented and said that he enjoyed kind of reliving his thesis and his honors project with you. So thanks for being here, Brian.
Yeah, it seems like so long ago. It was last year.
It's a different lifetime at this point.
I think there's like some sort of time dilation going on here, man.
Well, Dr. Malenda, I have a question.
Sure.
Dan, maybe we'll see if we have a few more from alumni rolling. Regarding the opportunities that are presented for students to do this type of research, are there other similar institutions to Moravian that also have access to this research site, or is it strictly just a partnership that we built as an institution for ourselves?
So I believe that because we use Skynet, I think it's North Carolina University has access to 35% of our telescope time as well.
Okay.
So that's kind of the trade-off with getting access to Skynet and having the ability to run these things remotely.
Sure.
But as far as I know, I think we're the only other college that has access to the observatory. Gary's nodding for me, so I feel better.
Okay, Peter, question from Peter. Peter asked, what data points or criteria do astrophysicists use to determine if exoplanets are likely to support life or not?
Oh, so it probably has to do with the distance from the star and how hot the star is. There's something called the habitable zone. And so if you're too close to a star, it's going to be too hot. If you're too far away, it's going to be too cold. And so usually there's a band where it seems reasonable that you might actually be able to have life survive under those conditions. And so that's at least one of the main criteria. And so that's why, like, the hot Jupiters, they're exoplanets, but they're probably not like exoplanets like we would think, oh, hey, that's an Earth we could go to and we could live there. That's not going to happen. They're too close, they're too hot, and we wouldn't survive something like that.
And another question from Jess, how do the filters work? I know on that one slide, you were kind of mentioning the different colors, the reds, greens, and blues. You know, is that something that you change and adjust on the telescope itself, or is that something that is kind of automatically adjusted?
Yeah, so you would choose the filters that you would want to take a look at for each telescope. And it seems a little misleading because your pictures are all going to look exactly the same in the different filters. You're not going to get a blue picture, you're not going to get a red picture. You're just going to get a regular picture that had the filter applied when it took the data. And so depending on what you want to look at and what you're interested in, you would choose the different filters that you would want to use for an observation. And so, for example, for us, when we were looking at the data that Phil had, having the information about the visible, the red, the blue, and the infrared was valuable because it gave us differences between the primary and secondary eclipses, and so between the two different stars in the system.
Thank you.
Oh, and Brian mentioned that liquid water is another thing, right? So if you're looking for a habitable planet, you want there to be liquid water, and that has a lot to do with the temperatures as well, right? So if you're too hot, your water is going to boil off, and if you're too cold, it's all going to be frozen for you.
A question from Dan, and maybe this relates to some of our other viewers tonight. Dan had asked if this presentation is going to be available at a later point in time. And I just want to let everyone know that's participating tonight that this presentation will be uploaded to our Return and Learn webpage with all of our other episodes from the previous 3 years as well. So make sure I will go and include a link in the chat right now for that page. But absolutely, if anyone is interested in watching this presentation later, you're more than welcome to do that.
And if I don't know if it would be helpful, but I can share my slides too if that's something that you would like to include.
All right, I was on mute. That would be great, Ruth.
Sure, absolutely. And I can stop this share. I just realized it was still doing that. I do a lot of Zooms, but not a lot of Zooms with PowerPoint. So.
A question from Ed. Do other wavelengths further outside the visible light spectrum come into play in those observations that you were talking about?
Yeah, they certainly could. So we mainly look at like ultraviolet and infrared outside of our visible wavelength range. But there's whole fields of astrophysics that look at other wavelength ranges. So I believe, did you guys hear about Arecibo this summer? Which was really, really unfortunate. It was this huge telescope, and it was in Puerto Rico, I think, and it collapsed. And that was a radio telescope, right? And so they actually look at what's going on in radio wavelengths, so really, really long wavelengths, well beyond the visible spectrum, and they can get other information about things that are going on in different systems based on those wavelengths. So there's whole areas of astrophysics that look at wavelengths well outside of the visible range. Yeah. Yeah, there's so much information out there, man. Like you can't even see it, but it'll tell you so much.
Yeah, it's pretty remarkable.
Yeah, I mean, it just kills me how much you can tell about these systems, and all you can see are these little dots of light, right? That's why the whole idea of the Doppler radar blew my mind so much, because you can't see that planet. It's not generating its own light. So you're not seeing it directly. You're just seeing how it affects the system, and the effects of that system are what you're using to get the information. And yeah, that it just is incredible to me. And I like it too, because it has big tiebacks to the theoretical atomic and molecular physics I do. All of the information that they get is spectral information, and they learn about how the molecules behave and how they interact based on the light that they emit. And so I really enjoy that aspect, because it doesn't matter if we're looking at stars or we're looking at atoms and tiny little molecules and things like that. It's the same thing same techniques that we're using to analyze this stuff.
Anyone else have any last minute questions? And if you'd like to ask Dr. Malenda a question offline, Ruth, can we provide your email and your contact?
Oh, sure,
info?
absolutely. Yeah, 100%. Yeah, I really appreciate everyone coming tonight. I really, really am glad you were here. I was glad to see so many friendly faces. It made my heart happy.
Well, we appreciate you being here, Ruth. Again, great presentation, and I appreciate everyone for attending tonight. Make sure that you keep an eye on your email for our last return and learn of the spring semester, happening May 25th with Dr. Beth Gottwalls from the nursing department. So when that email comes out and the registration comes out for that, feel free to join us for the last return and learn of the semester. And I hope that everyone has a great rest of your evening. Thanks so much, everyone. Take care.
Thanks, everybody.